Hello everyone. I'm from Korea. My name is Baek-Min Kim. Great to meet you. And Ji-hyun Oh and Gyu-ho Rim is my colleague, and actually Gyu-ho Rim is my advisor. Of Seoul National University, and this is our logo of Seoul National University. This research was collaborated by Florida State University and COAPS. This is the Institute for Ocean and Atmospheric Coupled Research. Stephen Koch and Dong Shin, this is a Korean colleague, are collaborating this research. Basically, this trip is first visiting of out of country, except for US. Yeah. So Taiwan, I just came to here first time. I like Taiwan very much these days. Yeah. But Ji-hoon said to me, when you come to here in summer, you maybe you don't have that good feeling. He said, but I think it's quite good place. Mostly the environment of the school is very good in compared to our Seoul National University. SNU is quite developing these days. Actually, we are in the middle of a mountain area, but it's quite developed. So these days we don't have trees, so I don't feel good. Yeah. And my topic is assimilation of stream precipitation into reanalysis and its impact on tropical divergence field. Our topic is basically considers the quality improvement of pre-existing reanalysis data. For example, ERA40 and NCEP R2. These two data sets are quite largely used in climate studies these days. But these two data sets have one caveat, because they don't use precipitation observation. So it's our topic, how it changes if we assimilate precipitation into the pre-existing reanalysis data, and how it changes its circulation related to the precipitation. It's our topic. This figure shows ERA40 precipitation minus global precipitation climate project precipitation, GPCP. And this is from ECMP website. The unit is millimeter per day. The blue shading shows ERA40 precipitation is bigger than GPCP. As you can see in the tropics, mostly in the ocean area, ERA40 data quite largely overestimate than observed precipitation. Yeah. We think that this is because they don't use precipitation as an observation. Yeah. Actually, they use quite large humidity variable in a simulation system, but they don't use precipitation directly. So we hope that if we assimilate precipitation directly in this ERA40 data, we hope that the quality may be improved. So, despite the importance of the direct heating related to precipitation to climate studies, the data assimilation system of long-term realists do not exploit the benefit of precipitation assimilation, as I mentioned. Inconsistency between the precipitation and divergence in existing analysis over tropics and subtropics has been demonstrated by Newman et al. This is a figure from Newman, BAMS 2000. This figure shows the observed precipitation, winter mean precipitation, and this is the NCEP, and this is a PRA15, and this is actually NCEP reanalysis 1, and this is the NASA model reanalysis. As you can see, there are very different precipitation, winter mean field. These figures are corresponding divergence field, upper level divergence field in 200 hectopascal. When we compare each precipitation and divergence, we can see the match between each reanalysis. We can see these cores here and here. EMA40, there is a here and here. The divergence and precipitation were matched within the reanalysis. We think human error refer to this phenomena matching between precipitation and divergence field called internal consistency. So each reanalysis has internal consistencies, but each reanalysis has a kind of external inconsistency. They are different, very different precipitation. So our motivation is that different models produce wide range of mean seasonal precipitation. Yet tropical SST, direct heating or forcing is a main ingredient for understanding climate variability and predictability. So reanalysis have a widely varying representation of ISO, such as MJO, and furthermore, MJO is a convectively coupled signature. So we hope that if we assimilate precipitation into reanalysis, we can improve MJO signature. And the tropical divergence for tropical cyclones significantly underrepresented in reanalysis dataset. The others have difficulties in maintaining ISO. So our object is assimilate the precipitation data to reanalysis using physical initialization technique and examination on the convectively coupled variability over tropics with the high quality PA reanalysis. We call PA reanalysis our product precipitation assimilated reanalysis. So the procedure is data preparation and preparation for assimilation, and test run and tuning of nudging coefficient. I will explain this one later. And production of PA reanalysis. And using this product, we will conduct diagnostic studies. And we use Florida State University Global Spectral Model. I will skip this portion. Assimilation method is based on the physical initialization procedure using Florida State University GSM. And rain rate is determined by the convective scheme. We use a poor scheme. It's a very simple poor scheme. And prognostic variables are notched using Newtonian relaxation toward the NCEP 2 reanalysis. Okay. This is a schematics of our analysis cycle. We prepare observation and background. We consider reanalysis 2 as a background of data assimilation procedure. And this background information is provided by dynamic nudging technique. It's a kind of relaxation. But observation is provided with this route. And observation is strongly relaxed, and the background is weakly relaxed. And we use precipitation and OIR data, and we use rain matching technique. Rain matching technique improves the vertical moisture structure. Okay, I will explain next slide this portion. So every time step, the observation is provided in this route, and the background is provided in this route. Yeah. So the continuously moderate quality of precipitation is improved. Rainfall matching technique is basically modifies the vertical profile of humidity as a function of the observed and predicted model rain rates. Through the continuous application of this technique, the model rain is brought closer to the observed rain rate. The humidity profile is modified using simple structure function to match model rain rate against train observation. This is mathematics implemented in the code. Here, RO is train rain rate at time t, and the RP is model produced rainfall using the convective scheme. And so at the time t, convective pool scheme produces rainfall. This is the RP. And Q is the specific humidity at that time. And then this equation says that the current humidity is modified like this. When the observed rainfall is larger than predicted, model predicted, then humidity is increased vertically. But this is a cloud bottom and cloud top. In the cloud top and bottom, there is a specific humidity, and inside the cloud, the humidity is reduced. Basically, this is proposed by the Krishnamurti, and when we continuously apply this scheme to model, then model continuously toward produce train precipitation.
Can you go back to the previous two? Previous one. I was kind of wondering why you have to use the trim data and the AVHR, because AVHR is not on the trim. And then for the remote sensing data, the TMI, trim microwave instrument data already been put in the trim precipitation rate. So what the purpose for use these two to do the observation part?
Since oral data,
but that's not from the trim sample. That's not from the trim. The AVHR is not from the trim.
Yeah. We just we get the main motivation of using oral data is that our Florida State University global spectral model also produces OERA because of radiation scheme, but it's quite unrealistic. So we just launch the model radiation to the observed one. This is our main motivation.
But from your presentation, you are telling us you are using the Florida State GCM to do the physical initialization.
Right.
I don't see the connection between this. You are talking about the soil GCM?
No. Florida State University GSM. Okay. So this our scheme is crude but effective, simple, easy to implement, and can be used to diagnose model errors, and no cost function to distinguish quality of data. But big assumptions are made that we control the humidity profile, which is just a 3D field using just a 2D field. So the results could be largely cumulus parameterization dependent. So this is the cons. Yeah. Choice of nudging coefficient should rely on painful procedure. Try and see. We have to nudging background using dynamic nudging. So we have to make a sensitive test to provide a proper background. So it's very painful test. So I will show you some preliminary results. First, I will show you the impact in the Western Pacific Warmth region, improvement, and tropical cyclone circulation, and ISO. So, excuse me, when should I terminate my talk?
We have about another 30 minutes.
Can I use more time? Yeah. The assimilation period is JJA 2000 and November 24. And we conducted the sensitivity to nudging coefficient. And 6-hourly analysis, this is the R2, and 3-hourly range are used. This is the trim. 3-hourly range are, the temporal frequency is important for the rainfall assimilation because diurnal cycle of convection is very important to estimate proper rainfall. So we use it's very lucky to have a 3-hourly trim range estimate. FSC GSM resolution is T63 and R27. To incorporate with this model system, we have to incorporate rainmate and analysis to this resolution. We have prepared. This is the NCEP R2 and trim. We use the trim MPA, multi-satellite precipitation analysis, 3B42. I will refer to this product as 3B42. 3B42 is a merged product of passive microwave product and microwave calibrated IR. And temporary resolution is 3 hour and partial resolution.
This data has no input from the PR, just TMI.
Yeah, just the camera. Yeah. This is the result. This is the November mean precipitation comparison. Because trim 3B42 is limited in -50 south to 50 south, we will show over that area. As you can see, the trim and our reanalysis matches very well, very close matches. Nothing to say more on this presentation. It's perfectly matched, as you can see. But this is a temporal. This is a snapshot of November 15. So this is a trim, and this is our product, and this is the NCEP analysis too. As you can see, in the tropical area, NCEP R2 tends to overestimate than trim and PAR. For example, this core is never shown in the trim. Here. So okay. There are large differences, but in the extratropics, NCEP R2 corresponds to trim well. So the problem is the tropics. But this is a temporal correlation with the trim and our PA reanalysis over November. So you can see that the correlation is very big. Green one and black one is a kind of a different product, but because our results are sensitively dependent on these nudging coefficients. So these blue, green, and black line correlation are calculated using different nudging coefficients. But our feeling is that the nudging coefficient does not, our research does not depend on the nudging coefficient severely. And this is the area average rain in the Eastern Pacific ITCG. As you can see, the red and black are very different in this region. We assimilated the trim 3B42 into NCEP R2, and we again examined August, May 1 to 31 August 2000. So we conducted first the sensitivity of nudging coefficient and compared ERA40 and GPCP intercomparative, and statistics are computed. So dynamic relaxation scheme is like this. Dynamic nudging provides background of precipitation assimilation. Suppose A is mother variable and A star. A star is a model prediction prior to relaxation. And then we apply nudging, then we produce A with the reanalysis data. So it depends on the nudging coefficient. When the nudging coefficient is getting bigger, then our analysis gets closer to the reanalysis more strongly. So we have to be careful because we want to improvement of circulation due to the precipitation analysis. So nudging coefficient should not be too strong. So we conducted sensitive testing. So we conducted 5 experiments. 8 means day inverse. This is actually proportional to the relaxation time scale. So this reverse of this is a time scale, E-folding time scale of nudging. So when we use 8, then its physical meaning is 3 hours. After 3 hours, the mother Brzezinski is relaxed toward the reanalysis. So when the relaxation coefficient is getting smaller, then weaker relaxation occurs. So first is most strongly nudged toward the R2 data. And second was divergence and temperature and Q, specific humidity are weakly nudged. Divergence, temperature, and humidity are very sensitive to the precipitation. So we reduced these nudging coefficient to see the impact of precipitation assimilation. And the nudge 3 is divergence part is more reduced. And nudge 4 is the temperature is reduced by the Q is reduced. So we prepared the 5 experiment set. So we calculated the statistics over the western Whampoa region. This region are indicated in this area. In this area, we calculated RMSE between trim and other products, and the standard deviation of each product, and the temporal correlation between trim and other products, and GPCP correlation with other products. Yeah. This is actually a tropical region, mostly Whampoa region, and as you can see, the ERA40 precipitation and the R2 precipitation, the temporal correlation between trim and GPCP are quite low, you can see, in compared to our product. And nudge 1 are strongly nudged, except for nudge 1, nudge 2, 3, 4 shows very similar statistics. So if we provide weak nudging on the divergence and temperature in Q, then it gives a quite good result. Okay. So one thing to note is that the trim and GPCP, the correlation, trim and GPCP is 0.6. Yeah. Because these two are observations, we expect more than this point, but it's a little bit lower than we expected. So first we compare mean precipitation, June, July, August mean. This is a millimeter per day. As you can see, the quite large difference between 342. This is a mistake. This is a 342. Most pronounced difference is Philippine Sea region and west of Bay of Bengal region and west of India. There are very big difference. In overall sense, R2 overestimates rather than 342. And this is a comparison between trim and our product, Nudge3. As you can see, Nudge3 is more similar to 342. These peaks are kind of matching. But you can see that there is one core in the frequency. Still, frequency core is remained. Because we use dynamic nudging, R2 is background for this simulation. The results are quite dependent on R2 itself. So this is influenced by that. But still quite reduced amount. And okay, this is these two figures are divergence of Nudge3 and R2. Mean divergence of 200 hectopascal. So this is the same figure I showed you, precipitation. When you compare R2 precipitation and R2 divergence, in the Philippine Sea, there is a large divergence period in the R2 data set. This is a very big problem because usually over the tropics, we can interpret the divergence, upper level divergence as a Russell wave source over most studies, Hoskins and Salvation, or they use reanalysis divergence as a source of wave activity. But this is a quite rather problem with it. Okay, this is a same figures, but I just show you some list information. I want to provide some information. We can compare the trim and GPCP. Trim and GPCP are quite similar, as you can see, but in this region, trim is a little bit strong. And one thing to note is that ERA40 data, ERA40 mean precipitation, when you compare the R2 and ERA40, in the tropics, ERA40 highly overestimates precipitation. Yeah. This was noted by, already noted by ECMWF scientists, and they give some bias correction. Yeah, this is quite a big problem. But divergence period of ERA40 again corresponds to each precipitation core matches, internal consistency. Okay, and this is a standard deviation. In the standard deviation field, R2 shows quite different than 342 and GPCP. again. Okay, I don't want to explain this figure in detail. Okay, so actually I draw the daily average precipitation at some particular point, interesting point. This longitude latitude is a region of a Philippine Sea, center of a Philippine Sea region. So I wanted to see that what's happened. So solid is 342 and gray is registering and dotted is R2. You can see that the R2 constantly overestimates in this region in compared to 342 over whole summertime in the 2000. So we are suspecting that the convective scheme over R2 is a problem scheme, but we didn't examine it yet. And this is one example that I prepared this figure that 342 and even GPCP in some region they are quite different. You can see that this region is okay. This is this point. In this point, standard deviation of 342 is very high, but GPCP there is no that characteristics. So I draw that this region times 3. And you see that this figure daily average the precipitation rate is over 150 in Trin, but GPCP is just 70 or 60 or 70. Yeah. Twice we largely estimate in 342 than GPCP. So we have to be careful to believe that 342 is quite just a true estimation of precipitation. It's dangerous. I think. Okay, I will see some tropical cyclone case. And I think I can show you just one figure. This is a Hurricane Bonnie and Charlie. This is Bonnie and Charlie. And this is the Florida region, and this is South America. This is a 800 hectopascal divergence field of NCEP R2 and our reanalysis. As you can see, the convergence related to the typhoon, cyclone, tropical cyclone, are quietly enhanced in our product. Okay. Next topic is ISO case. Actually, we finished to produce a long-term reanalysis product from 1991 January to 2005 31 December. These 3 settings are used, these settings, and to depict on the ISO signature, we did a composite based on Filler and Handel. Okay. We just conducted on wintertime MJO signature. This is okay. I'll skip this one. This is a strategy of our composite. Filler and Handel provided MJO index. MJO index is basically depicts the life cycle of MJO. So, for example, each day of a year can be put in this category, and we can average each day within the category. Then we see the typical feature of each page. So MJO usually in wintertime moves from Indian Ocean to Western Pacific. So when some particular day is in page 1, 2, 3, 4, 5, 6, 7, 8, it goes to eastward convective anomaly. So page 2 and 3 means that convective anomalies in Indian Ocean, and 4 and 5 is maritime continent and Western Pacific and Western Hemisphere and Africa region. So we calculated NOAA based on Pillar Handel Index. This is a longitude time section. We averaged 5 south and 5 north over composite pictures. This is a page, each page 1, 2, 3, 4, 5, 6, 7, 8. This is the longitude. So we can see clearly the NOAA weather clearly have a eastward propagating signal in the tropics. And our new reanalysis, this is a precipitation composite, and this is a precipitation composite of NCEP. Our new reanalysis shows the clearly eastward propagating signals, but the NCEP precipitation has a somewhat distorted, but has a some eastward propagating signal, but somewhat diverse feature. So, in particular page, when the MJO convective anomalies in page 3, we can see the circulation, composite circulation. So this is page 3, our precipitation assimilation realized rainfall, and this is page 3, NCEP rainfall. So convective anomalies in Indian Ocean. But you can see more clearly organized features are captured in our reanalysis data. Okay. And due to this convective anomaly, this is a 5 hectopascal of vertical velocity shading means vertical velocity. We can more organize the vertical velocity and more strong divergence appear in upper level here, yeah, in compared to reanalysis 2 data. Okay, now I want to summary. Actually, this is a diagnosis diagnosis using this product is in preliminary stage. So I stop here and I want to summary. The TRMM data is very well assimilated, and the associated model variables are consistent with the assimilated precipitation. Tropical Pacific rainfall and variability and its associated divergence circulation appears to be improved. Tropical cyclone circulation appears improved and more consistent with the independent observations. And ISO signature is much more pronounced in the PA reanalysis when compared to NCEP R2. And the meteorological variables such as divergence and vertical velocity of reanalysis are consistent with their respective reanalysis precipitation. So if the reanalysis rain is not correct, then we don't expect a good result. One possibility is like this. So this is just a possibility and a little bit exaggerated. Suppose reanalysis has a divergence here, and our PA reanalysis has divergence here. This can be a wave activity source, and loss wave, each divergence can generate more pronounced signature of loss wave train. And due to the lack of assimilation of proper precipitation, slather balance like this does not satisfy. So budget equation can be well satisfied in compared to PA reanalysis. But this is just a hypothesis. Yeah, it's very dangerous to believe this figure, but it can be possible. I just suggest. Okay, this is the end of my presentation. Thank you for hearing.
Any questions?
the schematics of our analysis cycle. These two sets are data set of our product. R2 is usually in data assimilation, observation and background should be provided because there are data void regions. We don't have a full 3D observations in atmosphere. So in data void region, we need inevitably depend on the background information. We use R2 as a background information.
So you use R2, the humidity, the velocity, the divergence.
And temperature and specific humidity. Yeah.
All from the R2.
Okay. Yeah. All data. But as I show you, this is a variable of R2. And as you can see, the nudging coefficients are different on different variables. So the nudging toward each variables are different. The intensity of nudging toward the R2, each variable are different because different nudging coefficients.
Did you mention that when you use a weaker nudging coefficient for the divergence temperature and shield to the humidity, then you got a better?
Yeah, right.
So I'm curious that when you use a strong nudging coefficient for the velocity and a weaker nudging coefficient to the divergence, then you got a better result. Then you use both stronger coefficients to these two numerical variables. And you have, I just want to know that, do you have more detailed response on this?
The motivation of choosing this constant?
Not the motivation, the difference.
Different?
Why you use a weaker nudging coefficient for the divergence is better than you use the stronger nudging coefficient.
Okay. As you see, the precipitation and divergence figure, difference of when we improve the precipitation, then precipitation is tightly related with the divergence field, upper level divergence field. So if we, in that case, if we nudge divergence field strongly toward the R2, we don't have a benefit of this precipitation assimilation. So that's why we use a weaker nudging coefficient for divergence field.
Have you ever compared the vertical profile of the divergence field after you nudge, after you so-called the data assimilation procedure? Vertical profile. Did the procedure modify the vertical profile?
I didn't explicitly check the vertical profile of divergence, but I just saw that each level of divergence field. But so in my feeling, the both lower level and upper level are intensified, but balcony structures divergence usually have the balcony structures when the convective signals appears. So more convergence and more divergence appears when our observation provides more precipitation than R2.
Maybe this has been too long, so why don't we, any question? So maybe a question from the students? Maybe we can ask question or continue discussion after we end the seminar first, okay? Let's thank the two speakers again.